Hello and welcome to Audi Service TV. Today we'll be looking at the new 3-litre V6 TDI bi-turbo engine. I'd like to welcome Wolfgang Mattes from Audi Service Training.
Hello, Thomas.
What will you be telling us about the new engine?
We will be taking a look at the technical data and the turbocharging function. In other words, the module. And we will be looking at the charging strategy in conjunction with the two turbochargers.
A second program will then cover the repair process and the active sound exhaust system. But now let's look at the technical data for the new engine. Where does the new engine fit in the V-diesel family?
The bi-turbo engine comes between the second generation 3.0-litre engine and the V8 TDI. The second generation 3.0-litre engine is the basic version. The torque band in the basic version is 550 Newton-meters. On the bi-turbo engine it is 650 Newton-meters, and on the V8 TDI it is 800 Newton-meters. The difference in power between the basic engine and the bi-turbo engine is around 50 kilowatts.
Technically speaking, is the basis for this bi-turbo engine the normal second-generation 3-litre V6 TDI?
Yes, that is the basis. However, with some modifications in terms of the mechanics, and of course with the bi-turbo module.
Self-study program 604 is available for the new engine. What does that contain?
It details all the changes compared with the basic engine. It also looks at the bi-turbo module and the modified components.
When we think of the terms bi-turbo or dual charging, we immediately think of power.
Yes, there is about 50 kilowatts more power.
We can see that expressed more precisely in this graphic. For a diesel engine, the engine speed range is extremely wide.
The engine is designed for up to 5,200 revolutions. The power is generated by the bi-turbo control. From 1,000 revolutions idling speed, it goes up to 4,200 to 4,500 revolutions. This gives us a power rating of 230 kilowatts. The torque is 650 Newton-meters. The torque is therefore present over a wide engine speed range.
The compression has also changed.
The compression has reduced from 16.8 to 1 to 16.0 to 1. This means you counteract the thermal load over the wide engine speed range.
What about the injection pressure?
The injection pressure corresponds to that of the efficient engine from the basic version. In other words, it is 2,000 bar injection pressure across the entire range. The highest value possible at the time is used.
Start-stop, recuperation and Euro 5 are presumably a matter of course.
Naturally, in order to reduce CO2 emissions.
Okay, so let's talk about the engine features. There are a few new components, and some components have changed.
The piston, for example, was not taken from the basic engine. The new piston features a piston pin bushing. This bushing splits the piston pin from the piston and acts as a slide. This reduces friction. The piston pin bushing features a profiled bore that changes its shape under thermal load when the piston expands. This keeps friction as low as possible. As a result, the material composition was also changed using a brass alloy. Another new feature is the complete cylinder head. The main difference here is in these cooling channels. The second generation has a connected cooling channel. All the coolant flows through this channel. On the bi-turbo engine, particular attention is paid to cooling the outlet valves and the injector. That is why there are two cooling channels, a lower and an upper cooling channel. These channels are separated by the cylinder head gasket. The flow in the upper channel is smaller than the flow in the lower channel. This means that these components that are subjected to severe loads can be cooled effectively. The camshafts are identical to those in the basic version.
What else is there?
This is the bi-turbo module with the two turbochargers. There is also a second charge pressure sensor. The particulate filter used to be installed close to the engine and is now installed away from the engine on the underbody. The reason for this is the lack of space due to the two turbochargers which are installed at the top.
It also looks different.
Yes, the large particulate filter has been split into two parts. This means that both filters can be installed in their original size on the underbody.
The number of post-injections has also changed, hasn't it?
Yes, there is a different post-injection strategy for the regeneration. There were 3 post-injections on the second generation engine. 2 injections close to the main injection and 1 away from the main injection. Now the third distant post-injection is split down again into 3 injection phases. This means that there are now 5 post-injection phases for the regeneration. The reason for this is the positioning of the diesel particulate filter. So there are a total of 8 injection cycles per work cycle.
You can look all of this up again in the self-study program. Now we come to the turbocharging function in the new engine. Here we can see the bi-turbocharger module. What are we looking at here exactly?
We're looking at a large number of components screwed together. Here is the familiar Vtg Turbocharger with the variable turbine geometry. The guide vanes are set in such a way that this turbine starts up early. This efficiently leads to an immediate high speed. Early charge pressure. The Vtg Turbocharger, as a high-pressure turbine, is slightly smaller than in the basic version. An extra turbocharger, a Wastegate Turbocharger, has also been installed at the top. This is the low-pressure turbine. Here is the control for the Wastegate valve, which is controlled via the vacuum unit. And here we have a very large vacuum unit. A lot of power is needed to control the turbine changeover valve. We will look at the function of this component in more detail later. The charge pressure is fed to the charge air cooler via this compressor bypass valve.
We have a 3-liter V6 TDI biturbo engine here in the studio. If you could run us through the components, Wolfgang.
Here is the Vtg Turbocharger with the variable turbine geometry. Here is the electrical actuator. Here is the Wastegate Turbocharger, the low-pressure turbocharger. The Vtg turbocharger is the high-pressure turbocharger, and this is the Wastegate control. The charge pressure is controlled using the vacuum control. This is the large vacuum unit for changing over the turbine. This unit is required due to the high levels of force. This new charge pressure sensor is also used to control the turbochargers. Out here is the compressor bypass valve.
There is another special feature inside. To show this, we have to take the module apart.
You can see that this is quite heavy.
Is it possible to replace the entire module in its installed condition?
Yes, you can replace it in its installed condition. The middle section of the plenum chamber, which runs along here, can be removed, so the mechanic can get to the components easily. Using these two eyelets, the entire module can also be lifted out by crane.
But for now, we'll do it manually.
Yes, you can do it manually, even though it is quite heavy. I will put it down here. I have removed the Wastegate Turbocharger. Here you can see the turbine changeover valve. Up here is the control for the vacuum unit. Here is the feedback unit. In order to control correctly, you need to know the precise position of the turbine changeover valve. The oil supply is controlled directly from the engine block. The oil pressure runs directly into both turbines, split in the upper part through two pipes. This means that both are connected to each other via one oil channel. The same applies to the cooling circuit.
We now come to a very small component.
When lifting the section out, I left this part behind. It is a shaped piece, which is mechanically coded using an installation position pin. The opening forms the shape of the turbine changeover valve. This means that the flap can close tightly here. It opens and closes like this. You can set the bypass in increments.
The shape confused me a bit.
The shape corresponds to the flap and allows it to close tightly. It isn't a butterfly flap. Instead, the flap is suspended on an arm and can only flap open and shut. This means it cannot jam, and it also seals more effectively.
What happens if you inadvertently fit the engine without this part?
You will notice that when you carry out the test drive. The engine will provide no power in the lower levels. Then you will suddenly get power from the large turbocharger, a typical RS2 effect.
Like the conventional turbochargers, first no power, then lots of power.
Exactly. Then you get pushed back in your seat.
But that doesn't happen on this bi-turbo engine. Let's take a look at the control strategy using a graphic. The torque curve should be even. It looks complicated, but it isn't really, is it?
It is easier to see in the graphic than in the tangle of components. You can see that the individual parts are switched in series. Here are the two exhaust manifolds, which run together via a Y-piece. Here is the Vtg Turbocharger with the Vtg guide vanes. Here you can see the turbine changeover valve. This is the one with the large vacuum unit. The flow of exhaust gas goes here to the Wastegate Turbocharger. In the Wastegate Turbocharger, the charge pressure is controlled via the Wastegate valve. The air drawn in is pre-compressed here. It flows through the charge air cooler. Then it flows through the throttle valve and, depending on the engine speed, through the swirl flap. This takes it to the intake area of the engine. As already mentioned, one of the charge air sensors is new. It can be found on the entry side, air side, for the Vtg Turbocharger. This sensor measures the overall charge pressure. As on all V6 TDI engines, it sits close to the charge air cooler.
The control works depending on the engine speed. Now let's take a look at the control strategy with the 3 phases.
There are 3 phases because of the different charge pressure controls in the system. In the first phase, 2-stage means that the Vtg and Wastegate turbochargers are working actively. The charge pressure is only controlled by adjusting the guide vanes on the Vtg turbocharger. That is this area here. The exhaust gases flow in here. The turbine changeover valve is closed. The exhaust gases flow over the turbine on the Vtg turbocharger. They drive the turbocharger to speed. The exhaust gases relax but also drive the Wastegate turbocharger. Now they flow out through the exhaust gas system. On the aspirated side, the air is pre-compressed at the same time. But that is not enough to open the compressor bypass. So the air flows to the Vtg discharger, which is already running at high speed. There the air is effectively compressed and flows to the intake side of the engine. This occurs at approximately 2,400 revolutions from idling speed.
What happens if you accelerate further?
If there is a higher load, the charge pressure is controlled via the turbine changeover valve. The Vtg flaps are completely adjusted. They are in the optimum position to provide airflow to the turbine. This is already running at top speed. Some of the exhaust gases are now directed to this turbine changeover valve. They drive the Wastegate turbocharger to speed. This compresses the air drawn in even further. The pressure of the compressed air is still not high enough for the compressor bypass to open. The Vtg with the turbine is operated again. The charge pressure is again very high at the top, but now with a higher pre-compressed power rating. This occurs in the range between approximately 2,400 to 3,400 revolutions. The charge pressure is controlled exclusively via the turbine changeover valve, no longer via the Vtg, as the turbine is already at full speed.
That is why there is a single-stage control at even higher engine speeds.
Yes, most of the work is taken on by the Wastegate turbocharger. The turbine changeover valve opens completely. This means that the exhaust gases flow past the Vtg turbine to the Wastegate turbocharger. This drives the large turbine with charge pressure from the full exhaust gas flow. The compressor bypass opens. The charge pressure is also compressed further here as the turbocharger is still running. It supports the effect. However, the highest charge pressure prevails here once the compressor bypass valve is open. That is why the pressure here is also higher than what the Vtg can achieve. The charge pressure can also be controlled via the Wastegate valve as in a petrol engine. The exhaust gases are directed past the turbine to the exhaust gas system.
We also have a little film, so that you can see precisely what happens. Here we see the engine.
Let's go into the module and pull it outwards in cross-section. Here we are in the first phase, as described earlier.
The speed range isn't fixed, but is rather a range.
Yes, this range depends on the temperature, load, position of the accelerator pedal and so on. It can also shift. The exhaust gases drive the Vtg turbocharger, and the turbine changeover valve is closed. After the Vtg turbocharger, the exhaust gases flow to the Wastegate turbocharger. This is the low-pressure turbocharger. The gases drive the Wastegate turbocharger, and a pre-charge pressure is generated. This acts on the Vtg turbocharger, and the power is provided accordingly.
Now we come to the second phase.
This phase is associated with higher speeds and loads. The charge pressure is now controlled via the turbine changeover valve. The valve opens slightly. Some of the exhaust gas flow goes to the Vtg turbocharger and drives it to speed as before. The rest of the exhaust gas flow goes to the Wastegate turbocharger. It drives the Wastegate turbocharger at a higher speed and therefore provides a higher charge pressure. But it is still not high enough for the compressor bypass to open.
That only happens in the third phase at approximately 3,600 revolutions.
Yes, from around 3,500 or 3,600 revolutions. That is at full load. The accelerator pedal is fully depressed and the speed increases. At higher speed levels, there is also a higher exhaust gas flow. In this phase, the pressure is still only controlled via the Wastegate turbocharger. The Wastegate valve is the charge pressure controller. The turbine changeover valve is completely open. All the exhaust gases flow past the Vtg turbocharger and drive the Wastegate turbine. The charge pressure is now so high that the compressor bypass valve opens. All the charge pressure is now provided to the engine. The Vtg turbocharger still receives charge pressure. However, the majority of the pressure goes through the open compressor bypass valve.
The Vtg simply keeps running.
It is always running and is also kept at top speed. This means that it is always available if required.
The turbine changeover valve and wastegate perform the key roles in controlling the pressure.
Yes, that really is the most important function. If this shape piece is missing, the RS2 effect occurs. Here you can see where the exhaust gases enter from the manifolds. This is the changeover valve in the same shape as the shaped piece. This is sealed by the large vacuum unit and is tightened by the vacuum, so it really is pressure tight. Because the path is closed, the exhaust gases flow here to the turbine via the Vtg. After the turbine, they then flow the long way round to the Wastegate turbocharger. If there is a leak here, or if the vacuum unit is incorrectly adjusted, then the exhaust gases take the direct route to the Wastegate turbine. The Vtg would not be driven at full power. This creates the RS2 effect.
Can we take another look at that component?
Yes, we can do that.
Then we know what the components actually look like and what they do.
This shaped piece sits here on top of the Vtg turbocharger. It closes off the channel so that the exhaust gases flow to the Vtg turbine. As soon as the Vtg turbine is fully actuated, we go into the next phase. The charge pressure is applied accordingly here.
We also have a graphic illustrating the charge pressure. We can see that the figures are quite high. Are they absolute figures?
On the left-hand side of the diagram, you can see figures such as 2,000, 2,400, 2,800 to 4,000 millibar. That corresponds to up to 4 bar charge pressure. The red line symbolizes the Vtg turbocharger. In other words, the smaller turbocharger. This is the high-pressure turbocharger. The relevant images are arranged here. The blue line is the Wastegate turbocharger. It needs high engine speeds to be able to produce charge pressure. At 1,000, 1,200 revolutions, we already have almost 2,800 millibar of charge pressure. The atmosphere has around 1,000, depending on weather conditions. At 1,200 revolutions, it is already 2,400 millibar. This figure rises to 3.2 bar as the speed increases.
Is there anything in particular to note when carrying out a repair at 3.2 bar?
When fitting the charge air duct, everything must be absolutely clean. The hoses, for example, must not be treated with lubricant for assembly. Everything must be installed dry, and you must work with the correct torque at the connections. Everything must be completely pressure tight at 3.2 bar. If anything is fitted incorrectly, a hose will fly off past your ears. The Wastegate Turbocharger always operates the VTG with the pre-charge stage. That is why it is able to produce charge pressure even within short speed ranges. At 2000 bar, you already have 3.2 bar charge pressure. The Wastegate Turbocharger requires engine speed, of course, in order to increase the pressure. The highest pressure is provided at the point with the highest power. At around 3,500 revolutions, the pressure rises above the charge pressure of the Vtg Turbocharger. This is the moment when the compressor bypass opens. Here you have the absolute charge pressure. The charge pressure is controlled via that of the Vtg Turbocharger. Any loss incurred on the long charge air duct is therefore compensated for. This leads to a constant charge pressure of approximately 3.2 bar in the charge air cooler.
We have lots of pressure and lots of torque, but also need a lot of cooling.
The cooler the charge air is, the less space it needs in the combustion chamber. The second charge pressure sensor is incorporated in the turbocharger control. It controls the function of the Wastegate Turbocharger. It measures what charge pressure comes from the Wastegate Turbocharger at the point of entry to the Vtg Turbocharger. In the charge air duct, it comes from the air filter through the large charge air cooler. This is made from aluminium and not from plastic, as is usually the case. As far as the material is concerned, it has been kept compact so that nothing happens. We then move into the engine's intake manifold via the second charge pressure sensor. This sensor is installed in every V6 TDI engine.
We know where the air comes from and know the torque and all the components. And we've seen how turbocharging works. In another program, we'll look at the repair process. We'll also look at the active sound exhaust system on this new engine. Goodbye. Until next time.